All right, let's go ahead and define Newton's first law of motion. Let's tackle that. All right, it says that an object at rest remains at rest, and an object in motion continues in motion with a constant velocity, all right, and in a straight line unless it experiences some net external force, something making it change what it's already doing. All right, this is simply going to stay still unless I make it move. If I do make it move, it's going to stay in a straight line at a constant velocity unless I make it or something else makes it change. Okay? Now we know that eventually this is going to come to a stop. That could be a change of hitting a wall. It could be on a very long runway, but it's going to stop because of the friction against the ground. All right? But that's the idea. Okay? The idea is if it rests, it's going to stay at rest. If it's moving, it's going to keep moving at the same speed in a straight line unless something makes it do something different. Okay? So that's Newton's first law defined. Write that down. All right? Keep thinking about our roller coaster question. Okay? What's going to happen to that car when it comes out of that loop and all the wheels fall off the car? Okay? One thing I'm going to ask you to jot down here is when the net external force on an object is 0, its acceleration is 0. Let's look at that. Ready? All right, same idea. Here's the ball again. All right, and it says when the net external force on an object is 0, its acceleration is 0. Well, right now it's pushing down on my hand, and I'm pushing back up on the ball, and it's the same amount of force. It weighs some amount, and so it's pushing down, and I'm pushing back with the same amount. Now, because of that, we have an external force of 0, okay? Some amount down, some amount up, they cancel out, and so it doesn't accelerate. It just sits there, okay? But as soon as I go ahead and change one of these forces, acceleration doesn't stay at 0 anymore, all right? So maybe I go ahead and change this external force from 0 to an upward force, all right? So I push on it. And now when I push on it and it rises up, now it's going to go ahead and accelerate, okay? Or let's just go ahead and take away the opposite direction force of my hand holding it up, all right? Now it's going to drop to the ground, and when it drops down to the ground, there's no force acting up on it, just a force acting down, and so there's nothing to cancel out, so I've got a ball that's going to accelerate. That's the idea, okay? Moving on, maybe. Hold on, my computer's sticking. Oh, whoops, there we go. Didn't mean to be on that screen yet. I told you. All right, here's the idea of that same thought about external forces, okay? Now, let's look at this little equation here. The little e on the left-hand side, that means the sum of, all right? That comes from math, okay? The sum of. The sum of F, the forces, when equal to 0, that whole idea, that whole concept fits perfectly with Newton's first law, okay? When the sum of all the forces acting on an object is equal to 0, that object is doing one of two things. It's either at rest or moving in a constant velocity in a straight line, okay? When we look at this, these painters here, all right, the painters, they weigh something, okay? And so does the scaffolding. Well, technically, that should be being forced downwards, and they should be accelerating down. But there's something causing the sum of the forces to equal 0. There's these upward arrows, okay? And these upward arrows are the tension on these wires holding up the scaffolding, all right? And so the tension on these is pulling up, the board and the guys are pulling down, and because all the arrows, all the forces that are in play here cancel each other out, we have a sum of all those forces equaling 0. What do we have as a result? We've got something at rest, okay? We see a little bit more tension over here than we do over here. Why is that? Well, that's because this guy's heading this way. The further he walks this way, the lower this one goes and the higher this one goes. Pretty simple idea, I hope. Okay? Great, it's going to stick again. There we go. All right, so we conclude that a body not interacting with its environment is either at rest or moving in a constant velocity. Okay? All right, Newton's first law has another name, and I just want to mention it. It's called the law of inertia. All right, so we got to define what's inertia. Inertia is the tendency of an object to resist any attempt to change its motion. All right, so think about this. One of these has more inertia than the other. The tendency of an object to resist any attempt to change its motion. Which one of these is going to be harder to get moving? Or, if already moving, which is going to be harder to stop? Okay, this one should be pretty obvious. Well, it's actually related to mass, okay? And so the one with the more mass has more inertia, all right? We'll cover that right here, okay? Look at these two wrestlers, all right? One has more inertia than the other. If the sumo wrestler, the big guy, if he gets moving, he's going to be really hard to stop, all right? But it's not going to be tough to stop this little guy because he's got very little mass, he's got very little inertia. If he's in motion, you'll be able to stop him pretty easily, okay? All right, so take a look. Mass is a measurement of inertia, and the SI unit for mass is the kilogram. We should know that from a while back, okay? More mass equals more inertia, less movement after an applied force. More mass, more inertia, less movement after I apply a force to it. Apply the same amount of force to this one as I do to this one, this sucker's going to get going, isn't it? All right, it's going to move pretty quickly. All right, we're almost done. A couple of practice problems. Ready? Consider a pair of forces, one with a magnitude of 20 and the other with a magnitude of 12. All right? What's the maximum and minimum net possible force with those two forces? So let's keep it simple. Let's just use me. All right? Let's say I apply a force of 20 newtons in, let's just pick a direction. Let's just say I go ahead and apply 20 newtons that way. All right? Well, it says what's the maximum net force possible between 20 newtons and 12? Well, the most would come from 20 and 12 moving in the same direction. All right, so I push with 20 and I got somebody else here pushing with 12. Now we're pushing with how much? We're pushing with 32, okay? The smallest amount of possible force using those two values would be in opposite directions. And so if I push with 20, someone pushes back at me with 12, we're going to use a positive on one of those and a negative on the other. Just thinking about, I don't know if you can see this or not, but remember, plus, minus, direction matters. Okay, and so 20 in one direction and 12 in another, we're looking at canceling out of most of it, leaving us with a minimum value of 8. Okay, so we'll see problems like this later, but now you just kind of have to understand when we consider forces acting on objects, how can we get the most out of those forces, or what's going to result in the least amount. All right, and then there's a second one, and it says there's painters and there's staging. All right, the staging weighs 300 and it's supporting two painters. Think back to that last picture. All right, one 250 newtons and the other 300. So we add all that up and we've got all this weight being pulled down, right? Now there's a scale attached to the left side of the staging that reads 400. What's the reading on the scale on the right hand side? I think I have a picture of this. I do. All right, so you got 400 on one side. This is really simple, okay? It's at rest, and so the sum of all the forces has to be equal to 0. If you have 250 down, 300 down, and 300 down, you add all that up, you get 6, 7, 850. Pretty simple. If we've got 400 being used on one side, you're going to have how much left over acting on the other side? You're going to have a total of 450 over on that side. All right, so this is Newton's first law. We moved kind of quick. All right, I want you to take some time after you've gotten these notes down, and I want you to go, and I've added a link. To our website. Okay, It's right next to it's right by the screencasts, okay? And that link is going to bring you to this screen here. And I'd like you to go ahead and watch this Newton's 3 Laws, Science of NHL Hockey. All right, we're going to look at a couple of these. I found these videos, and this one uses those laws of motion in NHL hockey, okay? So watch this. It's only about 5 minutes long, okay? All right. Coming back to this roller coaster, knowing what objects want to do unless they're forced to do otherwise, what's going to happen to that car when those wheels come off at the top of that loop? Okay? Is the car going to continue in that curved path, or does it fly off? Does it fly off in a straight line? All right, can you answer that question? I'm going to bring that back up in class and see where you go with your thoughts on that. Okay, what happens to that car when those wheels fall off? All right, think about what we just talked about. All right, that's Newton's first law. Hasta mañana.